Okay, in the last lecture, we talked about the so-called asymptotic analysis. It simply means we try to analyze our Java methods on the paper, assuming that the input can get towards infinity large. Basically, that's what we are considering. So you don't really have to run the program on a physical machine. You can just do some mathematical analysis. We'll see lots of examples today, just to complement what we said last time in the mathematical definition. But let's review the definition quickly. So in this course, you only have to worry about the so-called asymptotic upper bound. Specifically, we want to find the tightest asymptotic upper bound, big O. Okay, we'll get to that today for the rest of the lecture. And then you don't have to worry about something called omega, also something called theta. You'll learn about it later in the program. Okay? So what I will do is I'm going to review very quickly about the definition. Okay, just to remind you quickly, so we can start doing examples together. First of all, when you talk about big O over here, whenever you say it's a big O of something, okay, g of n is simply any arbitrary function. It can be n squared, it can be n cubed, it can be even log n, okay? But when you talk about big O of n, basically this is a set of functions that you're talking about. It's a family of functions. It's going to be just a set, okay, like a set with many things inside. And then you are given f of n, so this is basically your algorithm running time. You want to see what is the family it belongs to. Usually, a function may belong to many families. For example, conceptually, let's say, for example, okay, let me just mention very quickly. If I get f of n is simply just 2n plus 3, okay? So now, first of all, the tightest family it belongs to is the so-called big O of n, okay? So 2n plus 3 is just inside. Okay, that's the tightest family you can get into. However, every time when you grow the highest power over here, for example, you may also have big O of n squared. So you can also say 2n plus 3 is also belong to this particular family. That's also true, but it's not accurate. You can also say 2n plus 3 also belong to big O of n cubed. That's also true, but not accurate. So I want to be careful. Whenever you want to decide the asymptotic upper bound, you want to decide the tightest one. Okay? But how do you find the tightest one? The easiest way to tell is look for the highest power in your running time. Look for the highest one. In this case, n, which is power of 1. Okay? That's kind of what we said last time. But we're going to do more examples today. Again, that's a definition. So how can you prove? For example, if I want to prove 8n plus 5, so this is the algorithm running time. I want to prove f of n, which is an plus 5, is a member of big O of g of n. How do I prove it? Okay? According to the definitions, you only have to choose two things in order to prove. Okay? Number one, you have to choose a multiplicative constant c. And c is going to be applied to the g of n. Okay? Such that c times g of n can actually upper bound, which means it's larger than or equal to, and the algorithm you're talking about. So this particular upper bound effects, I'll call this upper bound effects. Okay, upper bound effects is going to be there starting from certain input size n0. As long as there's such an n0, you're okay. It doesn't have to be 1, it can be 2, it can be 3, it can be even 10. As long as there's such an n0, such that you can start having the upper bound effect, you're fine. Okay, that's kind of the definition we went through. Please review it, okay? And then let me give you one more intuition. How can you think of it? Again, this is what we said last time. Okay, again, let's see this. F of n is our algorithm over here, an plus 5. Okay? What I want to prove is f of n is big O of g of n. If you look at these two just for now, okay? Let's say if you look at big O, if you look at f of n, it's simply this line over here, which is somehow larger, well, it's actually higher, which means it will take more running time than this guy here. Okay, this is g of n. At the moment, g of n, without being multiplied to any multiplicative constant, it cannot upper bound f of n. However, we just have to choose some multiplicative constant c, such that it's going to happen. Okay? So what we do is, if you only look at g of n alone, it's not going to be okay. However, now let's say we choose the, remember according to the proof, we had to choose a C over here, right? So what we'll do is choose C to be, for example, 9. Okay, in that case, we're going to consider 9 times g of n. So now it's going to be 9n. The original g of n multiplied by some constant. So now what we get is exactly over here, the blue one. So now if you look at the blue one over here, it's going to be something like this. Okay, so now let's focus on these two lines. The first line is the original algorithm over here. The other one is the g of n multiplied by the multiplicative constant we have chosen. And now look at that over here. Before this particular point, before that, you can see before that it is the case that f of n over here is larger than g of n. So this is not where the upper bound effect starts, but it will start beyond this particular point. Because beyond this point, you can see over here, g of n multiplied by 9 is now larger than or equal to f of n for every input size. So that's where the upper bound effects occurs. Okay? That's how you should really understand conceptually. That's basically what we're doing for every proof that you're required to do. Okay? Guys, any questions so far just about the intuition? We're going to do the proof together. Okay? Any questions about this? Yes?
What if I chose the wrong C? Like, what if I just chose like 4?
Okay. After we talk about the strategy, you shouldn't actually choose the wrong C. We'll give you a strategy, of course. Usually C should be substantially large so that N0 exists at some point. Of course, if you choose the wrong C, that means you cannot complete the proof, right? Yeah. Okay, let's take a look. How can we do it? Let's have a look at, let me just tell you the strategy first of all, and then we do a very simple proof. It's very simple, okay? I don't want to bother too much of your time, but we got to do it. Otherwise, it's not complete for you. Let's say in general. So by the way, this strategy here does not include the case where your running time has log n. Okay? So that's some special case we had to deal with individually. But for now, let's assume the following. When you talk about your algorithm's running time is f of n, let's say we somehow arrange their highest power, their power from lowest to highest. You can see it's n to the power of 0, power of 1, all the way to power of d, from 0 to d. Okay? And then every one of them has some multiplicative constant, a0, a1, and ad. You can see the naming convention. For power of 0, the multiplicative constant is a0. For power of 1, it's a1. Okay? It's just a pattern over there. It's very general. So now let's say if your running time can be rearranged in such a way, and given this, what should be the tightest asymptotic upper bound? Okay? So here's a strategy. First of all, how do we decide the asymptotic upper bound, the tightest? You simply choose the highest power. Okay, so now you'll just be big O of n to the power of d. Of course, at the same time, it will also be big O of n to the power of d plus 1 as well, but that's not tightest, so it's not very useful. Okay? Let me just get rid of it. Okay? That's the strategy for deciding the asymptotic upper bound. First of all, just choose the highest power. Okay? But now, how do we prove it? Okay? Here is how you prove it. Okay? The way to prove it is two things. You have to choose a value for the multiplicative constant for C. For example, somehow get C times n to the power of d, right? That's what you're going to do. Okay? That's something we're going to do over here. And then you want to say also, how to calculate a multiplicative constant? It's going to be the absolute value for every multiplicative constant over here. The absolute value for A0, the absolute value for A1, the absolute value for AD. Okay? Why should that be the absolute value? Simply because sometimes you may have something like this. You may have 2n squared minus 3n minus 7. In that case, how do we choose C? It's going to be absolute value of 2 plus absolute value of minus 3 plus absolute value of minus 7. Okay? In that case, you will simply get 12. That's how you choose the C. Okay? You don't really include any negative number in the C. Okay? Number one. Number two, if you follow this particular proof, follow this particular strategy, and assuming that there is no negative number, assuming that there's no log n in your algorithm, then n0 is guaranteed to be 1. When there's log n, we had to deal with that specially, but we'll see example a little bit later. Okay, we talk about two things. Number one, what's the strategy of determining the asymptotic upper bound? The tightest, choose the highest power, number one. Number two, how do you prove it? You choose the C by summing up all the absolute value for the multiplicative constant. And then N0 is guaranteed to be 1 if there's no log n. Okay, that's the story. But I want to show you just one of the intuition. Why would this work? This will work if the following actually holds. Okay. Basically, we want to figure out if the upper bound effects is going to start when N0 is equal to 1. Okay? So now think about it this way. Okay? So now over here, basically f of 1, right? When N0 is equal to 1, we'll simply substitute n over here just by 1. Okay? That's what we're doing. What's going to happen if we substitute n by 1? It's going to be A0 multiply 1 to the 0 plus A1 multiply 1 to the 1 all the way to, and then we also got AD multiplied by 1 to the D. Are we okay with this? What I'm doing is I'm calculating f of 1. Okay? Having this, would you agree, is simply just going to be A0 plus A1 plus all the way to AD. Will it be okay? Okay, because 1 to the any power is simply just 1. And now, would that be less than or equal to 1 to the D? Let me see this. Am I getting something wrong here? You wouldn't be like that, right? Am I getting something wrong here? Okay, let me see this. I want to make sure this can be the upper bound effects for you. Maybe oh, you know what? Sorry about that. There's something I forgot in the formula. The absolute value sum. I didn't put it. Okay. Let me rephrase this a little bit. Okay. Beg your pardon. Okay. I should really fix the typo in my notes. We're going to consider the case where N0 is simply equal to 1. So that means f of 1. That part is not an issue. Okay. It's going to be less than or equal to, if you recall the definition, it's going to be over here, C multiplied by G of n. I forgot a C. Sorry about that. Okay. Let me put a C in the context. So, okay. What I should do, what would be C? Exactly over here. Okay. So now it's going to be A0 plus A1 all the way to AD. Okay. Multiply, what would be G of n? In this case, it will be 1 to the D. So what are we ending up comparing? We are really comparing the following two. Okay? We're saying A0 plus A1 all the way to AD. Would that be smaller than or equal to their absolute value sum? Always, right? For example, let's say over here, for example, let's say in this case, A0, okay, this is 2, minus 3, and minus 7. If you think about it, here, this simply just a sum of all of them together, right? So that'll be 2 plus minus 3 plus minus 7. It's a guarantee to be smaller than or equal to the absolute value sum. It will be, right? So that'll be less than or equal to absolute value of 2 plus absolute value of minus 3 plus the absolute value of minus 7. It will be, right? So that's check. Okay? So that case there can be easily proved. Basically, we want to show that the upper bound effect will start right from n is equal to 1. Okay? That's the case. And then the second one, I'll refer you to the slides. You're going to be done in a similar way. The second one, you basically want to show that when n is any arbitrary value that's larger than or equal to 1, and then you're also going to have the upper bound effect. In this case, of course, it's going to be c multiplied by n to the power of d, where c is this value over here. Okay? Should you memorize the proof? Not really. We are just trying to show you the strategy. Of course, for those of you who are curious about why the strategy works, that's the proof. Okay? Again, to use it, you have to make sure when you choose C over here, it must be the sum of the absolute values. Okay? And then N0 will just be 1 for sure. Okay? Any question about this? Okay? at least you should know how to determine the tightest upper bound, number one, and number two, how to choose C and N0. Okay? All right. If no question, let's do some application by using the examples. Okay? Okay. So now let's see this. Different example. Before that, let me just say one more thing. How do you interpret whenever you say big O of G of n? Okay? It's going to be a set of functions. So that's why one of you asked me before, if I simply got, right, similar. If I got, for example, 7n plus 2, okay? Let's say this is my algorithm function, okay, the running time, 7n plus 2. Apparently, the highest power is simply just 1. So for sure, 7n plus 2 definitely belongs to here. It also belongs to all the big O family where the power is strictly larger than the highest power over here. And of course, it also belongs to over here. But which one should you say? You should choose the lowest one, the tightest one, which is big O over n. Okay? Again, you should really have this mental picture here. Big O of n is going to be one family over here. And then with a strictly larger power, for example, big O of n squared, it's just going to be a superset. Okay? They are not exactly equal. There will be something, for example, over here. 2n squared minus 7. If you look at this particular function here, it can definitely be upper bounded by n squared. How do we prove it, by the way? How do you prove that? This is definitely big O of n squared. Let's apply right away. What C should I choose? Should I choose minus 5? 2 plus minus 7? No, 2 plus absolute value of 2 plus absolute value of minus 7, right? So choose C to be 2 plus minus 7 absolute value, you will get 9. And that's guaranteed to be, starting from n0 is 1. Okay? So for this particular one, it's going to be big O of n squared. However, it's not big O of n. It doesn't matter how large the C you choose, because the highest power is strictly smaller, so it's not going to work. Okay, so far it's really about pure math, but we're going to see how interesting it is to apply this to the code. So given certain fragment of code, maybe with some loop, we want to see exactly what the running time is. And then we're going to do some interesting case studies today by doing some sorting. Okay. Any question about this before I move on? Okay. All right. Okay, let's do example. Okay. Basically, the example I'm going to do one by one. Okay, just to make sure you're really comfortable with the proofing, the proof steps. Okay. Okay, there's something we already set already. Okay, the table. Okay, this one, the proof we just did. Okay, I'll make sure I fix the typo for you. Okay, so you don't get confused. I'll make sure. Okay. Okay, and also there's something we set. It's about the family relation, right? Strictly larger superset relations. Okay, that's also set already. Okay, let's do more example. Okay, I'll do one by one on iPad. Okay, let's try to get that. Number one, let's say this is our running time. 5n squared plus 3n log n plus 2n plus 5. What should be the tightest asymptotic upper bound? N squared, would you agree? Because, easy, highest power is here, okay? Not surprisingly, n squared. Now, that's an easy part. How do you prove it? So now let's prove it. I'll show you exactly how you can prove it, and then that will be the standard we should apply, for your written answer later. How do you prove? Okay, so now you got to choose two things. The multiplicative constant for n squared, something over here, and also n0 should be something. Okay, I'll put question mark just for now. Such that C multiply n squared, which is the family we are trying to prove, right, is larger than or equal to 5n squared, I'm just copying that, plus 3n log n. And if I didn't say the base, you can assume base 2. Okay, for this course, it's not base 10, base 2. Plus 2n plus 5. This is some relation you want to show eventually. Okay, so now, what C should I choose? Well, according to what we said before, right? Just add up the multiplicative constant, right? What should you add up? 5 plus 3 plus 2 plus 5, for example, right? So now 5 plus 3 plus 2 plus 5. So we get 8, 10, 15. So now, can I safely put 1 over here? That's the question. Let's try. Maybe, maybe not. If C is simply just 15, okay? And then N0 is simply 1, so now let's replace that by 1. So 15 times 1, so we got 15. Is it larger than the right-hand side? Let's try. Again, N is simply just 1 because we talk about 1 here. 1 to the square, so 5. Plus, now, what should this be? 0. Why? Log 2 0 is log 2 1 is 0. So guys, make sure you understand log base 2 1 is 0. Because 2 to the power of 0 is 1. Okay? If you have trouble with this, talk to me after class. Okay, I'll help you a little bit. Okay, I assume you know. Okay. And it's going to be log 1 over here is going to be 0. 0 times whatever is going to be 0. And plus 2 times 1, 2, plus 5. It's going to be 12. Okay? Good. Any question about this? Every proof we'll try to do later is going to follow the same procedure. First, see the highest power, and then choose C, choose N0, typically just 1. However, you want to convince me or convince the grader that the upper bound effects is really going to happen starting from N0 being equal to 1. Okay? Question first. Yeah, then I'll come to you. I would say yes. Wouldn't be so tricky, right? If we do put this kind of question, I think that the example I'm going to go through with you, and plus the one you're supposed to do for lab A, they should be sufficient. Yeah. Do you need any calculator in exam? You should be able to add this up, right? If you really got trouble, yeah, sure, calculator is fine. Yeah. I don't think you need it. Imagine you're just wasting your time in the exam, right? Yeah. Anyway, the answer is yes. You may bring calculator if you want it. Yes.
So when does it work for N0?
Very good question. What if, because here, in this case, we're lucky. Even though we got log n, but it turns out, according to this equation here, for this particular case, N0 can be 1. We'll see one case very soon when it doesn't work. Good question. We'll get there. Okay. Okay, that's good. It's only a warm-up for you. Let's try another one. Number 2, okay. How about this guy here? Okay, first of all, what should be the big O? N cube, okay, very good. Highest power. How do we prove it? Okay, I'll start you off. Again, you want to be very natural about doing this. Proof. You want to choose C to be something, N0 to be something, presumably 1, but it may not be the case. And then you're going to say such that C multiplied by N cube larger than or equal to, and now let's, and then we say 20 N cube plus 10N log N plus 5. Okay? How do we choose the C, first of all? Well, add up the multiplicative constant, right? Let me do that. So it's going to be, over here, 20 plus 10 plus 5. 35? Now the question is, can N0 be 1? Well, if you're not so confident, let's do it, okay? So that means 25 multiplied by, and then we talk about N being 1. 1 to the cube, just 1. Is it larger than or equal to 20 times 1 to the 3, okay? Plus, now you can see that it's already 0, right? So this part is simply 0. And plus 5. Well, since we are lucky again, fine. Right? 20 plus 5, 25, right? Okay. Guys, we okay so far? Okay. Let's see. We might eventually end up being unlucky, right? Again, N0, if without any log n, it's guaranteed to be 1. If with log n, you got to be careful, okay? Let's see this guy here. What should this guy be? Log n. Well, basically log n is still more expensive asymptotically than constant, okay? Okay, log n. Now, can we follow the same proof procedure and see what happens? Okay. What I would do is, let's try this. Okay? Be careful with this one. Proof. Again, choose C to be something over here, and then also N0 to be maybe 1, maybe something else, such that C multiplied by log N larger than or equal to, these are going to have the upper bound effects, 3 times log N plus 2. Okay? What C should we choose? 5, right? According to the formula, the strategy. Well, add up the multiplicative constant. That part is not hard. 3 and 2, okay? You just have 5. Now, the question is, can we choose, can N0 be 1? That's the question. Okay, for those of you who realize it's no, let's see why, and then we'll see what should we choose. Okay, let's try. Be careful. So C is 5 multiplied by log 1. Okay, we'll talk about N0 being 1. Is it larger than or equal to 3 times log 1 plus 2? Hopefully you already see that's not the case because this guy here is 0. This guy here is also 0. Is it 0 larger than or equal to 2? No. So N0 over here is not right. So N0 was chosen wrongly. Okay? So that's the case where I said, in general, log N doesn't quite fit into that formula. So you got to be careful. So now, what should we do? Well, choose a larger N0. Okay? Why don't we choose another one? What if I chose over here, let's say N0 to be 2? Would that work? Yes. Maybe yes. Let's try. Of course, in the exam, don't say just say yes. You got to show, right? How do you show? Okay. Let's see over here. Okay, again, I'm going to apply this general form. Okay, let's do it together. So now, C will still be 5. 5 multiplied by log. So now N will be 2. 2 base, okay, by the way. Larger than or equal to 3 multiply log 2 plus 2. Since we're lucky this time, right? We're getting there. So now, log 2 will be 1. Log 2 will be 1. Is 5 larger than or equal to 3 plus 2? Yes. Now we are fine. The main lesson from this particular example is when you have log N, don't be so happy to just choose a multiplicative constant sum and then say N0 should be 1. It may not be. Okay? So you got to be careful. Any question about example number 3? Okay. Does it make sense to you? This one? Okay. All right, let's see the next one. We got 2 more, I believe. Yeah, either 1 or 2 more. Okay, and then we're going to see a little bit more code. So far, we're just playing with the equation a little bit, just to get you comfortable. Okay, number 4. How about this guy here? What should that be? It seems to be, it's not really like a polynomial, right? It's like exponential, right? So that's a worst case. Exponential basically is the worst kind of algorithm you can have. It might work, but maybe very slow. Okay. Okay, so now, okay, I can tell you the answer is exponential. But now, how do I get to this part over here? From this guy here, just to 2 to the n. Basically, would you agree? 2 to the n plus 2 is 2 to the 2 multiply 2 to the n. Okay, so that's the multiplicative constant we are talking about. Okay, just a little bit trick. How do we prove this? Again, the same thing. Okay, I'll write down a little bit. I'll let you complete the rest. It's very easy. Okay, so now how do we prove it? Proof. You have to choose C to be something over here. And N0, you will hope it is simply 1. I'll put a question mark just to be a little bit reserved over here, right? Such that C multiplied by, over here, 2 to the power of n should be larger than or equal to show up upper bound effects. 2 to the power of n plus 2. In this case, of course, we'll talk about N0 being 1, 1 here, and 1 here. Okay? So now, what should we choose for C? What should we choose? 4? Yeah. Exactly, because we already rewrote the formula a little bit, so that's a multiplicative constant over here. So you can just say 2 to the 2, which is 4. And now, I will leave it to you to complete the rest to see whether this 4 over here can make this whole inequality true. Okay? You can do the math. Okay? It seems like it can, right? All right, guys, any questions? We okay? Okay. All right, oh, since I got one more, okay. One more. And for this one here, just to save a little bit of time, okay, should it be, what's the highest power? Log n or n? N, right? N actually grows steeper than log n, okay? Okay, n, very good. So now, similar proof strategy, okay? I would suggest, I'll leave this part empty for you, so when you review the iPad notes, feel free to do it. Print it out and do it. But when you see the slides, okay, that's basically what we're doing over here. And especially for the third one, when one doesn't work, right? I also have an explanation there for you. So now, when you do, for example, this guy here, which I just showed, okay, it will turn out to be, you can simply choose 1 or 2 and also 1. I'll leave it to you to see why it would be the case, right? You gotta outline the inequality as I did for all the previous example, right, to show that it is true, okay? That's about it. Okay, we're seeing quite a number of examples so far to really get you familiarized with the process. Okay? Questions? Okay? All right, let's move a little bit further. Okay, so you want, oh, again, this is repeating. You want to get as close as possible the tightest upper asymptotic upper bound. For example, if this the highest power is 3 over here, so you would say it's n big O of n cubed. Okay, you wouldn't say it's n to the power of 4, even though it's correct, but it's not accurate. Okay, most accurate. Okay, so now, so these are the common classes of functions we'll see. That's the cheapest, constant. Okay, if you can have your algorithm that's both correct and also constant performance, that's the most ideal. Okay, log n is the next. So what we will see maybe on Tuesday, the last class, I'm going to show you some algorithm that'll be log n, so-called binary search. Okay, I think you also want to know about it quickly. Okay, we'll get there on Tuesday. And also we got linear. Linear is also very, for example, if you want to find out the maximum out of an array, that will be linear. Intuitively, you may have to scan the entire array in order to find out the maximum. Okay, you're going to do that. And also n log n, this is also something we'll see on Tuesday in the last class. It's about sorting a list of integers. But we'll show you something that may not be as efficient, which will be n squared. Okay, we'll see that first. Okay, and then n cubed as well, and then etc. Okay, finally you got exponential. And this diagram over here is also very important over here. So this one basically shows you that, I'll help you read it a little bit. The horizontal axis over here is the size of the input. You go from 10 to the 0, 10 to the 1, 10 to the 2, all the way to 10 to the 15, the input size. The vertical axis over here is the running time, okay? You can see this guy over here that grows the quickest, this guy here, right? So that's the exponential, which means you really don't want to have an exponential algorithm. That means even with some reasonable input size, you're already running out of resources, basically, just running too slow. On the other hand, if you look at over here, okay, I'll try to show you a little bit over here. The one that's at the bottom over here, right? That one's very steady. That's kind of the so-called constant algorithm, which means always remains stable, regardless of the size of the input. There's one more thing I want to point to you. If you can see this another second line over here, just slightly steeper than the constant one over here. I'll try to move my mouse over here. You can see that one, just above the blue one, okay? I'll point to you again. This one here, right? You can see the blue one? That's right above it. That one is a log n, which is also very nice, okay? Just slightly more expensive than constant. Okay, so these are the common functions you want to get used to, okay? And then I would say these are the typical running time you'll run into, okay? Okay, so now we're going to do coding a little bit. I'm going to give you a series of examples over here, and then we don't really have to calculate the precise number of primitive operations anymore. What we will do is we're going to look at the code and then just give you sufficient information to do some analysis. Okay, let's see. Let's do one by one. Okay, the first one. Basically, I'm calculating an algorithm. I want to do the running time for this. Given two parameters, x and y, I simply want to know what's the maximum of x and y. Okay? Overall, what's the running time? What's the tightest asymptotic upper bound for this? Would it be linear, constant, log-in, exponential? Constant. Also, usually if there's no loop, you can quite safely say it should be constant, right? Over here you can see, let's see how we can figure that out. This guy over here is mainly about primitive operation, right? How many? One? Oh, actually, it's simply just a single assignment, okay? It's big of one, basically, right? And it's only to compare the condition, right? The condition. So that's also big of one. And also another single assignment is also big of one. And return, also big of one. Overall, big of one. What does that mean? That means it doesn't matter what the values are for x and y. This max will always take the same amount of time. Doesn't matter how large x and y's are. It does not depend on their size. Okay. Running time does not depend on how large x and y are. Okay, constant. Okay. Also, usually the very first program you do in Java, to print a hello world, that's also a constant time algorithm, right? You always do print out. Doesn't matter how. Actually, it's even more constant. Okay, second one. How about this guy here? Well, that looks familiar, isn't it? Right? That's something we did last time. Last time what we did was we simply tried to calculate the precise number of primitive operations. Maybe it was 7n plus 2 or something like that. Okay, you can look it up. Well, something like that. Okay? Let's say this. If this is the first time you're seeing this without calculating the precise number of primitive operations, how do we tell? Okay, let's have a quick look. Let's see line by line to see the pattern. Okay? And later on we might see some nested loop, okay, which you have to do for lab 8 as well. Number one, over here, what would be the running time for this roughly? Constant, right? Array indexing and also assignment. Okay, basically big over 1. Constant. Okay? Since now the purpose is not to calculate the precise number of primitive operations. So just tell me whether it's constant or linear. That'll be enough. How about this guy here? How many times? Well, apparently only initialize just one time. How many times are we going to execute this condition here? N. That's to be precise, right? But now, just linear, big over n. Okay? And then we know that I is going to be from 1 to all the way until n. Right? For each one of them, we're going to execute this particular if statements. Well, that's the body of the loop, right? That's the body of the loop. This one here is simply comparing some condition. So this one over here is big of 1. And this particular one here is just another assignment and array indexing. That's also big of 1. And I++ is I plus 1 and then assign. That's also big of 1. It seems like the body of the loop for each iteration is going to be constant time. So you can think about when I is equal to 1, it's going to take constant time. When I is equal to 2, it's also going to take constant time. Similar until when I is equal to n minus 1. That's the last iteration. Okay? It's also going to be big of 1. If you add them up together, big O of 1 plus all the way to 1. How many 1s do we have? Roughly n. Big O of n. It's a different way of deriving the running time. It's not really being informal. I'm just saying we don't really worry so much about the precise number of primitive operations. Yes, questions?
So if it's like two loops, like a nested for loop or something, would it be n to the power?
Good question. Will a nested loop always give to you n squared? No, not really. I'll give you one example right away. It's a very important question. I didn't expect this early, but I'll talk about it anyway. The question was this. Will a double nested loop give running time bigger of n squared? Okay, in general. The answer is no. I'll give you a counterexample. What if I say for integer I is 0, I, let's say less than n, that's fine. Okay, let's say n is some array size, okay? I plus plus. This part seems to be fine. And then I would say for integer j, use a different loop counter, is, let's say 5, I less than 10. Oh, not I, sorry, j. J less than n. Oh, not n, sorry. 20. Hmm? Oh, yeah, sorry, what I'm thinking. Sorry, I'm tired. I'm tired. Everybody's tired. J plus plus. Okay, like that. Okay, and then over here you might say print something. Okay, doesn't matter. So now, apparently, you can see we got double loop. Would that be quadratic? Not really, because over here, you can see over here, it's always running exactly 5, 6, 7, 8, 9. So 5 times. So this part over here is always going to be constant. So constant times linear, so it turns out this guy over here would just be linear. Or even, if I try slightly different, slightly, what if I say, rather than n, I'll change that to 10. It's not even linear. It would be overall constant, right? So now I know some of you might tend to be a little bit lazy. You just see how many nested loop I have. So I will just give you the power of that. It's not going to work always. Okay, be careful. Okay. All right, let's go back here. Okay, let's see example number 3. All right, things now will start to get a little bit more interesting. Okay. Well, apparently we got a nested loop. So now it's, as we just said, you don't want to make a conclusion right away. It's going to be n squared, even though it could be, but may not be. Okay. But what would be the running time for this?
This one is n squared because it has the variable instead of the constant.
That's true. You definitely you don't have a constant as an upper bound for sure. But now, how do you derive that, right? Depends on how we ask you the question. If we simply tell you to specify the state, the tightest asymptotic upper bound, you can say n squared. That might be okay. But we might want you to show we might want you to show the work, the derivation process. That's what we're more interested. Okay, let's see. Without any reservation, let's see this. How do you answer this kind of question in general? You want to observe the pattern for the loop counter. That's my advice. Okay, the general advice is like this: observe the pattern of changes on loop counter. So this is a principle I want you to remember, the pattern. How do we observe the pattern? You have to derive a little bit. I'll show you. Okay? Let's say for this guy here, let's start with the first line, second line. Okay, we know that I is going to be 0 and then all the way until I less than n. And don't forget, it's I plus plus over here, right? Okay, what would be the pattern for I? I would just be 0, you'll be 1, you'll be 2, all the way to n minus 1, agree? Okay, n minus 1 will be the last one because when I is equal to n, you don't really satisfy this. So you already exit from the loop. Any question about the pattern for I? which basically just observe what's the initial value and what's the maximum value, and how large do you make a progress, every iteration, okay? Let's see, and then let's have a look at the body of the for loop over here. This guy here, the pink one, okay? What's gonna be the pattern over here? Again, we got another loop counter. J will be starting to be 0, less than n, and then j plus plus, okay? So now that means over here, for every iteration, for every possible value for I, we have to worry about the pattern for j as well, okay? That's why it's pink. Let's say for the very, when I is equal to 0, what will be the pattern for j? J will be from 0 until n minus 1, agree? And also, when I is equal to 1, j will be from 0 until n minus 1. Similarly, j will be from 0 until n minus 1, and also j will just be 0 until n minus 1. Somehow the value of somehow the value of j does not depend on I. But we will see some example where it does depend. It'll be a little more complicated, but that's okay. So that means for every value of j, we now have to worry about what's going to be the running time for that. Okay? So now we have to look at over here. Okay? Let me use another color here. So the body for the nested loop, the inner loop, is over here. The green one. What's the running time for that? Just the green one, basically line number 4 and line number 5. What will be that alone? 1. Because over here, this is logical operation, and that's relational operation, just adding them up, right? So this part over here, just this line will just be big O of 1. What about return? Also big O of 1. So that means for every value of j over here, we are simply just going to execute something that's going to be big O of 1. Okay? For every one of them. So now, how do we add up everything together? Okay? So now, that's how you can think of it. Just for this particular one, when I is equal to 0, and throughout all the possible value for j, what will be the aggregated running time? Basically, big O of 1 plus big O of 1 all the way to big O of 1 for n minus 1 times. For n times, actually. Yeah, that would just be big O of n. One more thing I want to make sure you're okay. Notice one minor detail over here. You can see we say j starting from 0. And the last value for j is simply n minus 1, right? n minus 1. If you say j is from 0 all the way until n minus 1 inclusive, how many possible value of j we are talking about here? Is it n minus 1 or n? N. Okay? How do you tell? Okay, a very basic formula I want to mention over here. Okay? Whenever you talk about the size of the interval, I'm pretty sure you learned about this in calculus maybe, right? If you got starting value I, ending value j, and both being inclusive, right? So what would be the size of this interval? J minus I plus 1. Okay? Double check this formula. Okay? I assume you know about it. Okay? So now, every possible value of j, we're going to execute this particular body of the code, of the loop over here, is going to be big O of 1. And how many iterations do we have? N iterations. Okay? That's why we got big O of n. So now, big O of n, for every possible value of I would be how many possibilities? From 0 all the way to n minus 1. So now we got n. Okay? So now overall we're going to get big O of n times n. Okay? N squared. Let me make a little bit notes, and then I can take your questions if you got any. Okay? The n over here is about the number of iterations for, I would say, for I, the outer loop. And over here, this will be the number of iterations for j. And then, if I just might write times 1, okay? So that can be more complete. So this 1 over here is simply the running time for line number 4 and line number 5. Line 4 and line 5, because they're simply just primitive. Okay? That's how we aggregate everything up. Yes?
So like if the inner loop was more
Complicated?
yeah, the more
We'll see in the next example. Yeah. You might be thinking, for example, let's say for line number 3, rather than saying j will just be initially 0, what if I say j is initially I, for example, right? Would that change the running time? Intuitively, you would think, because it seems to be maybe fewer iterations to be run. But now since we talk about asymptotic, right? We'll see the next example. We'll see exactly that. Okay, we'll get there. Guys, any question about this? This one, simply the main message here is to say, given the loop over here, you want to analyze a pattern for the changes on the loop counter. If you got 2 counters, analyze both of them. If you got 3, analyze 3. I believe for your lab number 8, you got 2 loop counters. Okay, it's not that hard, but we're going to see enough example in the class so you can do it. Okay, I assume you're okay. So let's see another one over here. And, oh, not yet. Okay, maybe we'll see it in the next one. How about this one here still? Number 4. This one, you can see we got 2 loops over here. One is not nested. The other one is nested. Does that mean we're going to get n cube? Not really, right? They're going to run one after another. So their running time should be added up rather than multiplied together. Okay? For this one, we can do a little bit more quickly. I just simply put things together, right? Let's think about it. For this one here, so it's going to be, first of all, line number 2. That one is going to be constant. Okay? And then this loop over here, you can see we're simply going for n iterations, right? And then for each iteration, it's simply going to be constant, right? This is going to be constant and for n times. So big O of n. And then how about this guy here? It's going to be big O of 1. How about 7 to 9? Would that be linear? Would that be quadratic or constant? Any idea? This is pretty much similar to what we just said previously, right? So I'll leave it to you. You can see for the first loop counter, it will simply run n times. For each possible value for j, you will simply run another n times for k. And for every iteration inside over here, it will be constant time. Okay? Overall, it's simply going to be O of big O of n squared. Overall, it's going to be like this. Big O of 1 plus n plus 1 plus n squared. And only the highest power matter. Okay? Big O of n squared. Okay, that's just another example. Yes?
apparently the first loop runs forever because there's no
Oh, interesting. Aha.
That's a syntax error.
It's you know why it's interesting? It's a typo. Forever. Yeah, actually, if there's no upper bound. Oh, you know what? Interestingly, usually when you do this kind of runtime analysis, you don't necessarily consider termination. So that when you actually think about I is only smaller than n, in that case, you will think about how many times maximum you can actually run the loop. You don't necessarily worry about termination. Yeah, but you actually, I really meant to put I plus plus, for sure. Yeah? Okay, sure.
So,
Thank you.
and this means like the exact number of operations would be not be n. For the first will be n minus 1. Exactly, but we're not concerned about that.
Yeah, so again, so when we ask you the question, it depends on how we ask you about it. If we say only to determine the tightest asymptotic upper bound, then the way I do it will be sufficient. If we explicitly say you have to count the precise number of primitive operations, in that case, you have to do what we did on Monday. Yes, it depends. But I believe for your lab number 8, I didn't say you have to count the precise number of primitive operations, so you don't have to. Right? Yes, it really depends. All right. Okay, guys, any other questions about this? Yes. In the real world, would you ever have to calculate a precise number of primitive operations? No. However, before you can really move to the case where you can sketch the analysis, like what we're doing over here, you better know how to count the precise number first before you can do the more rough analysis, right? Yeah. All right, let's see the next one. All right, that's going to be the final one before we see some case study. How about this one here? This one already highlight to you what you should really pay attention to. In line number 4, you will simply say J is initialized to be I, right? So now, would that actually reduce the running time, or it would just be the same? But why would that be the same, though? So over here, of course, intuitively, you might think it will be just the same. But you want to prove it, right? You want to show it, right?
Because it doesn't matter, we're not determining the precise number of operations.
Well, it is true when we are saying we are not really determining the precise number of primitive operations. That's true, but still your analysis has to be rigorous. Still has to be. Somehow, I tell you what do I mean by rigorous? You still have to show the pattern for the loop counter to show me why it will still be bigger of n squared.
Yes, but for example, if we had like just j instead of I just equal to 5, for example.
Okay.
The complexity of it is still n.
True.
So it doesn't matter what we put for j, the complexity will still be n.
But I would say you're not trying to prove for general. You just want to focus on this particular example. Yeah. Yes.
The number of iterations is something like n times n plus n times n minus 1 plus n times n minus 3.
We'll get there. Somehow you're just telling me exactly something that's going to be calculated, right? We can see that. Yeah. Okay, let's see how we can analyze this. Okay? Again, you're going to see line by line, and then once you get to the loop, you have to analyze the pattern for the changes for the loop counter. Okay, let's see. Line number 2, easy, big O of 1. Okay, and then over here, I would suggest we try to see the pattern for the loop counter quickly. Okay, I is going to be 0, and then all the way to n minus 1. And apparently, it's going to terminate, right? So termination is not an issue over here, right? So now we can see I would be simply 0, 1, 2, all the way to n minus 1. Okay? Not n, because n will make it false. Let's see what's going to happen when we get to the in the loop over here. Okay? So now we want to see how exactly loop counter is going to change. Okay? When you can say j is the initial value is simply going to be the current value of I. So now, what about j over here? It will just be 0 to start with, right? So it will be from 0 all the way to n minus 1. Agree? And then, what about when I is equal to 1? So that means j will be from 1 until n minus 1, right? You can see the 1 here corresponds to the 1 over here, right? When I is equal to 2, j will be from 2 until n minus 1. It's getting a little bit different from before. It's not exactly n, one moment. And then over here, you can see j would be basically from n minus 1 until n minus 1, right? Still something to be done, but it seems like the amount of work we have to do is decreasing every time, right? Intuitively. Yes, question?
So isn't this just n divided by 2 times?
Not quite. We will see. We'll get there. First of all, is everybody comfortable with the pattern I'm trying to derive over here? Okay, good. Having that agreement there, let me see one more thing, okay, before we try to do a little bit of math, okay? It's not difficult math. For the body of the loop over here, let me use a different color here. This guy here, well, would you agree, is simply big O of 1, right? Indexing, and also some plus, and also some assignment, big O of 1, okay? So that means for every possible value of j, you'll just do big O of 1. Okay, so it's constant. So now the question is, how do we aggregate all the running time up? How do we do that? You want to say something?
Would this be
n log n? No. Typically, when you will get, I'll tell you what, I'll give you a little bit of intuition. We'll see on Monday next week. You get log n when you're trying to shrink the size of the input by 2, but that's not the case over here. Okay? N factorial is too much. Too much. It turns out this will just be, oh, say something, yes. It's like a series over here. It's like a geometric series, arithmetic sequence. Which one? Let's see. Okay, let's see this over here. Number one, let's see this. Let me use different color here. When I is equal to 0 over here, what's the amount of work we have to do when I is equal to 0? We know that j will be from 0 until n minus 1. How many iterations are we talking about? N. Good. It's just n. And each one of them is simply constant, right? It's n. What about the second one over here? When I is equal to 1. N minus 1, agree? Because it's from n1 until n minus 1, so n minus 1. If you go with the pattern over here, so this will be n minus 2. All the way to the last iteration where I is equal to n minus 1, 1. So now how do we add this up? For those of you who received some education from elementary school, you should know this, right? I hope. Maybe not elementary school, sorry. Maybe junior high school, maybe. Let's see. N plus n minus 1 plus all the way to 1. Okay? What's the formula? Oh, yeah, exactly. N plus 1 multiplied by, how many terms do we have? N terms, right? Divided by 2. And you don't even need to simplify that. You can see n multiplied by n. You already know the highest power will be n squared. So you can say it is big O of n squared. Of course, feel free to simplify that, and then you realize by dropping all the lower terms and multiplicative constant, you get n squared. Guys, please make sure you're comfortable with this, because if you are, lab A should be a piece of cake for you. Should be. I hope. Any questions about this? I hope you're fine. Yes. Yes. What should you write in the lab? Okay, that's important. In the lab, I would say you somehow have to show to the TA that the pattern of the loop counter can be observed in such a way that you can conclude, I can do n plus n minus 1 plus all the way to 1, and then I got this particular series. That's what the TA wants to see.
Do we also have to explain like why, for example, line 2 is all 1?
I would say do that as well, yes. Because eventually, good question. I haven't really completed the story yet. What we have done to be big of n squared was only for this guy over here, okay? Just to make it clear. This guy here is big of n squared, and this one is big of 1. And don't forget, there's another return, which is big of 1. But they are simply lower terms. They don't really matter. So eventually you can say this term here dominates. So that's the eventual answer. Okay? Loop is usually a tricky one. Okay. For those of you who really want some very challenging exercise over here, which I chose not to put for Lab 8, if you want to do it, come to my office. I'll give it to you for a personal challenge if you want to do it. Okay? Feel free not to be marked. All right. Any question about this, please? Okay. I believe the next one over there would be to talk about some sorting. Okay. So I got about 15 minutes. I would say I'll save this guy here maybe for Monday. Okay, I can do that. Okay, that one there. I want to do the more interesting bit together with you today. Okay. I want to do two kinds of sorting, at least at a conceptual level. The code is given to you, it's working, okay? I already tested it. I'm skipping just one slide just for today. Only this slide here I'm skipping. I will come back here next time, okay? But I want to go directly to a case study quickly. We talk about sorting. Sorting is a very fundamental problem in computer science. Given a list of objects, you want to sort it in a particular order, okay? We talked about comparable before, right? Remember arrays that sort? Arrays that sort, what kind of a sorting algorithm they are using? I can tell you, it's neither of the sorting strategy we talk about today. Neither. It's something called merge sort, which we'll do next Monday. That was n log n. Okay? But now, what I would like to do is, I want to give you a conceptual idea how these two sorting strategies work. Okay? They make sense. And I'll also show you the code. And then we may not have time to analyze the code complexity, but I'll do that maybe next time. Okay? Okay, again, the problem is we want to sort a list of integers into from lowest to highest, okay, in a non-descending order. Selection sort, okay? I will switch the iPad and talk about it. There are two sorting strategies we're going to talk. So these are the two most basic sorting algorithms. By the time you graduate, you should know about at least 5 sorting algorithms as a CS major. Selection sort, insertion sort are 2 of them. Okay? You may have heard about bubble sort before, but we don't cover that in this course. Okay? Bubble sort is not the way to go. Okay, selection sort first. One thing at a time. I'm going to use one example to illustrate to you. Let's say we got this particular array as input. Okay? Size 4. 3, 1, 4, 2. Not sorted. Eventually, it should be sorted into 1, 2, 3, 4. Okay? Easy problem to illustrate. Okay? What's the strategy in general? You're going to do the following. Okay, thinking this way. We're going to divide, conceptually, the array you're trying to sort into 2 areas. One is called the unsorted area. Initially, everything is unsorted. You can think about the unsorted area occupies the whole array. And then, eventually, we want everything to be green, eventually. Okay? So, in the middle of your selection sort, you're going to see half red and half green, basically, right? That means you're making progress. And what's the strategy over here? Here's the strategy. You're going to keep selecting the minimum from the unsorted portion. For example, initially, this is the unsorted portion. Choose the minimum. In this case, 1. What do you do after you choose 1? After you have chosen it, you have to append it to the end of the sorting portion. Over here, you can imagine initially the sorting portion is simply just over here. It's simply just empty. Okay? That's conceptually how selection sort works. But now I'm going to show you how exactly that works. Okay? But the code, I'll show you the code as well, but a little bit later. Let's see this. Let me just copy this one here. We're going to have several steps to do. Okay? So now, follow this. Choose minimum. Minimum is, initially, this is a minimum, right? So now you can imagine, after the first iteration of the selection sort, we're going to basically insert the minimum that we just chose, which is 1. 1, and then everything else maintain the same order. 3, 4, and 2. Conceptually, how do you understand that? You can understand it like this. So that means the only sorted portion is over here. Whereas this is still unsorted. You can think about every time you try to make a progress for the iteration, you're growing the green area and shrinking the red area, hoping that eventually the red area will be empty. Okay? So now, how do we make the next progress? Well, according to the algorithm, you have to choose the minimum from the unsorted area. 2. Okay? And then, so that means you're going to do this, and then remember we already got 1 over here, right? So now 2 is the minimum we chose, and append that to the end. And everything else remain to be the same, 3 and 4. Okay, so now this part over here is sorted. And this part over here is unsorted. I guess so far, you can see the color, right? I just want to give you some intuition. The code itself is doing exactly that. You're just going to do a little bit more tricky programming there. Okay, let's do one more. Okay, and now if you do the next iteration, you can imagine what I'm going to do. Basically, I'm going to choose minimum 3 over here, and then append it to the end of the green area. So that means I'm going to get 1, 2, and 3. Okay, and then 4 is to remain over there, right? So after this, so that means now I got 1, 2, and 3, and then I got 4. Okay, I'm basically done. Because now the unsorted portion has only size 1. It's already sorted, right? So eventually that's how I sort the array. Now the question is, what will be the running time for this? Do you think it's linear? What's the costly part for a selection sort?
Going through the array and looking for the minimum.
Yes, exactly. Exactly. Conceptually, this is how a selection sort works. I will try to be a little bit more general for you. Selection sort goes like this. If you have an array that's unsorted and the size is simply just n, What would be the cost to choose a minimum? N, big O of N. After the first iteration, only the first element is sorted. And then you still got the remaining part, which is N minus 1. That's not sorted. What would be the running time to search for minimum out of N minus 1 elements? Big O of N minus 1. Imagine I keep shrinking the area for the unsorted version all the way to, eventually what you will get is, finally, this is the only one that's unsorted, right? And constant time, because nothing to do. Okay, so now it would be something very similar to what we just did. N plus N minus 1 plus all the way to 1. What would that be? N squared, right? That's the arithmetic sequence we just talked about. Okay, big O of N squared. Okay, any question about this? Initially, this, sorry, let me get the color right. Unsorted over here, unsorted, and then this is unsorted, right? Sorted and sorted, just to make it complete. So that's the concept. You can see I don't give you any code. I'm just describing how the algorithm works. Even by that, you already know what the running time is. That's the advantage of doing this on the paper. Okay? Any question about selection sort? Okay, let's do insertion sort. Insertion sort works in a way very similar to selection sort. Insertion sort means the insertion part is more expensive. In the case of selection sort, inserting just means appending to the end. So there's no work to be done. Okay? How about insertion sort? Insertion sort simply means we simply pick something from the unsorted area and then insert that to the right place in the sorted area. And you did something like this in one of the labs. If you can tell me which one it is. Recursion lab, which method? Something called insert into sorted array, right? That's exactly this step. I didn't tell you at that time. Okay? For those of you who might be interested, look back in your lab number 6. Insert into sorted sequence is exactly what each step it is for the insertion sort. But let's look at that. Okay? So now let's see how things work. Keep getting the first element from the unsorted portion. When I say getting, no work. Basically, just getting it. Okay? And then inserting it to the sorted portion so that the sorted portion is grown but remain to be sorted. Okay? Let's see how that might work. Let's see this. Number 1, I'm going to get a new array over here. Okay? The new array over here. So now I will just pick one element. Oh, just pick the first one. Okay? The first one. Now I want to insert that into the green area so that the area has become size 2, but it's still sorted. So where should I sort that into? Before 3, right? So now that means it's going to be 1 and 3. And then the rest remains to be 4 and 2. Okay? So now after this, this is the green area that's sorted, and this is, oh, sorry, and this is unsorted. That's the first iteration. Insertion is expensive. When you get to the part where the sorted area is so large, right? Okay, I'll write some general analysis for you in just a moment. What about the next one? What will be the next iteration? For the next iteration, we're going to choose the next one from the unsorted version, 4. How do we insert 4 into this particular sorted area so they remain to be sorted? It turns out, just append to the end, right? Well, basically, the way you do it has to be, can it be here? No. Can it be somewhere in the middle? No. So it has to be go to the end. So you're going to run a loop to decide this, right? So after this, you're going to get 1, 3, and 4, and 2 remain to be there. So now after that, what you will get is this is sorted and this is unsorted. Unsorted is only size 1. It's as if it's sorted. So now, what will be the running time for insertion sort? Linear, quadratic, cubic? I'll give you a little bit hints. The formula that you're going to end up having will be very similar to this guy here. Very similar. But in the reverse order, if you see what I mean. Okay, let's see why. Thinking this way, let's say we start with this particular sequence over here. Oh, let me just use maybe blue. Blue would be better. let's say this is the sequence we start with, okay? Let's say that's how we start with. And then when we start with, we simply got this part over here to be unsorted. And this part over here to be, oh, sorry about that, the other way. This part to be sorted, and this part over here to be unsorted, okay? And the sorted area is simply of size 1, okay? And then we simply pick one element from there. What would be the running time in order to decide whether it should go to here or here? It's constant, right? Just 1, basically, right? Either it should go here, we go there, okay? It's only 1. And if you go to the next iteration over there, you have grown the size of the sorted area by 2, into 2. So that means it's over here. And then we got over here. So now, what will be the running time, the second one? Basically, you have to think about how many iterations do you need. You choose this one over here. Should you go for here? Should you go for there? Otherwise, you go to over there, right? So maximum, you might need 2 iterations to decide. All the way to, what would be the last iteration? The last iteration will look something like this, okay? Let's see this. The last iteration would be when the sorted area basically is so large. Let's see this. Let me just give you 2 here. Let's say this guy is already sorted, and over here it is unsorted. Okay? How do we complete that? Basically, you have to basically choose the first element over here, and let's say the size of this is simply n minus 2. So now, how do you insert that into this particular size of the sorted portion? How many iterations do you need? Basically, roughly n minus 2, right? Basically, just correspond to it. Okay? When you have 1 element, you just need 1 iteration. If you have 2 elements, maximum you need 2 iterations. When you have n minus 2, that means in the worst case, you may have to go all the way, and then to the end, you got to insert that at the end. Okay? So that will be n minus 2. And now, how do we aggregate the running time over here? Well, it's going to be big O of 1 plus 2 plus all the way to n minus 2. That's basically similar to this guy over here, right? Just in the reverse order. So what does that mean? When you are doing selection sort, the first step is the most expensive. You got to choose the minimum from like an n minus 1 size array. Whereas in the case of insertion sort, the last iteration is the most expensive because it's basically almost sorted. The last element to insert into it will take longer to actually insert into the right place. Okay? Selection sort versus insertion sort. Okay? Big O of n squared. Okay? That's the answer. Hey, any question about this? This kind of analysis is really valuable. You can see, again, I'm not showing you any code just yet. I'm only describing the idea. Just from that, we can already tell what's going to be asymptotic upper bound. So you don't need to see the code. But we'll definitely show you the code a little bit, maybe next time. Okay, next week will be the last class. Make sure you come. We'll talk about maybe the exam. Okay, see you next time.